According to a study of TV viewing habits, the average number of hours a teenager watches MTV per week is population mean mu equals 19 hours, standard deviation sigma equals 3.8 hours. So notice immediately that we're provided with the population mean and the population standard deviation. If a sample of 64 teenagers is randomly selected from the population, then determine the mean and the standard error of the mean of the sampling distribution of the mean. I know it sounds long-winded, but it's simply using the it's basically asking us for mu sub x bar, which is the mean of the sampling distribution of the mean, and sigma x bar, which is the standard error. So we're going to use our definitions for mu sub x bar and sigma sub x bar. The mean of the sampling distribution of the means is always equal to the population mean. So we always have this relationship. Mu sub x bar is always equal to mu, no matter what. And we saw this earlier. If you added up all the column that represented the sampling distribution of means, we added them all up and divided by the total, we got 68, which was the same exact number that we got for the population mean. So you'll never really have to do any work when asked to find the sampling distribution of the mean of the sampling distribution of the mean, when you're provided with mu, because it's the same value. So mu sub x bar, the mean of the sampling distribution of the means, is equal to 19 hours. Okay, the work comes when you have to find the standard error. The standard error is found with the formula sigma divided by the square root of n. Okay, so the standard error, which is denoted by sigma sub x bar, is equal to sigma divided by the square root of n. So we read our problem again, and we take a look and we see that sigma, our population standard deviation, is 3.8, and then we're told that our sample size is 64. So since our sample size is 64, that takes the place of n in our formula. So what we do is we simply take 3.8 divided by the square root of 64. So 3.8 divided by the square root of 64 on your calculator, you should get a value 0.475, and if it does not terminate, you should always take the standard error out to 4 places. This particular example terminates, but if it does not terminate, take it out to 4 places, just like any standard deviation. So to answer questions like this, you need to spot the standard deviation for the population, and then you need to spot the size of the sample. Okay, and then you simply apply the formula. Standard error is the population standard deviation divided by the square root of the sample size. Example 8.4. The registrar at a large university states that the mean grade point average of all students is mu equal 2.95 with a population standard deviation of sigma equals 0.2. So we have the population mean and we have the population standard deviation. Part A asks us to determine the mean, mu sub x bar, and the standard error, sigma sub x bar, of the sampling distribution if the sampling distribution mean consists of all possible sample means from samples of size 25. Okay, so I had said earlier that sampling distributions can be created with samples of any size. In this particular problem, the sampling distribution is being created by looking at all possible samples of size 25. So every possible sample of size 25 is constructed, and using that n equal 25, little n equal 25, we can use that in the formula to find the standard error. Part B says determine the mean and standard error of the sampling distribution if the sampling distribution mean consists of all possible sample means from samples of size 100. So in this case, our sample size is now changing from 25 to 100. So it's becoming a larger sample. Okay, so we are going to do the formula for the standard error twice, one with little n equal to 25, and the next time with little n equal to 100. And then we're going to take note of those two numbers. What effect did increasing the sample size have on the mean and standard error of the sampling distribution? In which sampling distribution would you have a better chance of selecting a sample mean which is closer to mu equal 2.95, and why? So when we see the word better chance, we should think about probability. So this last question is asking us, in which sampling distribution, the one described in in part A or the one described in part B, would we have a greater chance, a greater probability of choosing at random a sample mean closer to the population mean 2.95, and why? Okay, part A, we are asked to find the mean and standard error of the sampling distribution. N is 25. So to find the mean of the sampling distribution, mu sub x bar, we simply just note that mu is 2.95, therefore mu sub x bar is also 2.95. The mean of the sampling distribution is always the same as the mean of the population. The standard error of the sampling distribution is going to be found with that formula, sigma divided by the square root of n. So we take 0.2, which was the sigma that was provided in the problem, and we divide by the square root of the sample size, which was given to us as 25. So 0.2 divided by 5, because the square root of 25 is 5, that's something that you could do without a calculator. And then 0.2 divided by 5 should give you 0.04. Okay, again, if this was not terminating, then we would take it out to 4 places. So our standard error is 0.04. So the mean of the sampling distribution is 2.95. The standard error of the sampling distribution is 0.04. Okay, we're going to change our sample size from 25 to 100. The mean of the sampling distribution, mu sub x bar, is the same as the mean of the population. That does not change when you increase the sample size, because by definition, the mean of the sampling distribution is always the same as the mean of the population. It doesn't matter what the sample size is, it's always going to be 2.95. The standard error, we're going to apply the formula, sigma divided by the square root of n. So we say 0.2 divided by the square root of 100, and we know that square root of 100 is just 10. So 0.2 divided by 10, and that becomes 0.02. The standard error is 0.02. So note that when we put in a different sample size, in this case a sample of size 100, which is 4 times greater than a sample of size 25, the standard error changes. What effect did increasing the sample size have on the mean and standard error of the sampling distribution? So what effect did it have on mu sub x bar? What effect did it have on sigma sub x bar? Okay, so if you take a look at what mu sub x bar is, in both cases, it's 2.95. When n is 25 and n is 100, mu sub x bar is still 2.95. When you look at what the standard error is, when n is 25, the standard error is 0.04. When n is 100, the standard error is 0.02. So what effect did increasing the sample size have on the mean of the sampling distribution? Nothing. You change the sample size, you do not affect the mean of the sampling distribution. What effect did it have on the standard error? It it decreased the standard error, 0.04 to 0.02. Increasing the sample size decreased the standard error. So increasing the sample size had no effect on the mean of the sampling distribution, mu sub x bar, but increasing the sample size from 25 to 100 decreased the standard error from 0.04 to 0.02. In general, this is always going to happen. As the sample size increases, the standard error of the sampling distribution will decrease. Okay, this is always going to happen. If you increase the sample size, take note of what happens with a fraction. If you increase its denominator, you're going to make that fraction get smaller and smaller and smaller, okay? If you keep increasing that denominator to be bigger and bigger. And that's why the standard error will eventually get smaller and smaller. Now let's remember what a small standard error is. A small standard error, very similar to a small standard deviation, means that there's not a lot of variability in your data values. When dealing with a sampling distribution, it means that there's not a lot of variability with the sample means when the standard error is small. So that's going to help us to answer question D. In which sampling distribution would you have a better chance of selecting a sample mean closer to mu equal 2.95? And why? So let's review the significance of a small standard deviation versus a large standard deviation. Smaller standard deviation indicates the values are more clustered about the mean. A large standard deviation indicates that the data values are more dispersed or spread out away from the mean. So in which case would you have a better chance of selecting a sample mean closer to mu equal 2.95? It would be the one with the smaller standard deviation, which in this case is a smaller standard error because more of our data values are clustered about the mean. So a good ideal answer would be the sampling distribution of the mean for all possible samples of size 100, when n is 100, would give us a better chance because more of the sample means are closer to the population mean in this case. Okay, when you create samples of size 100, you create multiple sample means that are generally closer to mu. Whereas when you created samples of size 25, the sample means were further away or more dispersed than from mu.